Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 34 on the subject of computer organization and assembly language programming. Well, the title of today's session is Memory Addressing Modes. Well, this slide shows today's agenda with different addressing modes that we are going to study today. And at the very end, you will be able to have a very clear understanding of x86-64 base, index, scale, and displacement addressing mode. Well, before I define the addressing modes, this is the general format of an assembly instruction. An opcode field which specifies the operation to be performed, and then one or more fields that specifies the operands. If I talk about x86-64, the instruction size is variable and can range from 1 to 15 bytes. Although theoretically you can construct instructions larger than 15 bytes, but normally they are illegal. Well, dear students, in assembly language programming, the term addressing mode refers to the way in which the operands of an instruction are specified, which can be immediate values, registers, or memory locations. An operand field provides the location where the data to be processed is stored. Different processor architectures support different addressing modes. As far as x86 is concerned, x86 instructions vary in the number of operands. However, most instructions use two operands with the first operand as destination in case of Intel syntax. Well, these are the combinations that are typically legal. Register to register, register to memory, memory to register, immediate to register, and immediate to memory. And remember, memory to memory operations are not allowed. Well, let us move on to the first type of addressing mode that we are going to discuss today, that is implied addressing mode. Dear students, in implied addressing mode, the operand is specified inside the instruction opcode. Well, the zero address instructions are designed with this sort of addressing mode. And these are some of the examples, like CLA instruction means clear the accumulator register. CMA instruction means complement the accumulator register, and so on. Well, the stack-based instruction, for example, add means take two operands from the top of the process stack, add them, and place the result back on the top of the stack. All these instructions use implied addressing mode. Well, as far as the advantage of implied addressing mode is concerned, since the operand is not encoded inside the machine code, so the instruction size is very small. The next addressing mode I'm going to talk about is the immediate addressing mode. In immediate addressing mode, the operand is directly provided as a constant within the instruction itself. For example, these are the instructions which we have seen in the previous session as well. The immediate value 3A in hex is moved inside the AL register, and over here this immediate value 123 in decimal is moved to the EAX register. Remember, since we are using a 32-bit register in 64-bit mode over here, so the upper 64 bits of the RAX register will be zeroed out, while this will not happen in this case. And I think I have talked about this in the previous session, where I have talked about the move instruction, the details of the move instruction. Well, these are the pros and cons of immediate addressing mode. This is fast since there is no memory reference, and this is the limitation, that is the range of the constant value depend on the total number of bits of the operand field in the instruction. For example, if we keep 8 bits inside the instruction for this immediate value, you can have an unsigned constant ranging from 0 to 255, or a signed constant ranging from -128 to +127. After immediate, we have the register addressing mode. Well, in register addressing mode, the operand is present inside the register, and the register number is actually encoded within the instruction itself. If you consider this is a register file having 16 different registers having the number 0 to 15. So inside the instruction, if we have two register operands, the number or the code of the register is mentioned inside the instruction. These are the examples of moving the contents of register ECX inside EAX, and this add instruction actually adds the contents of RAX and RCX and place the result inside the RAX register. Once again, you need less number of bits to encode the register as compared to the memory address. This is the advantage. As I've already said, if there are 16 registers, only 4 bits are required to encode any one of these registers. And last but not least, the speed is better as registers can be accessed far quickly than the memory. The next addressing mode is the register indirect. In register indirect addressing mode, the register contains memory address of operand rather than the operand itself. So if you consider this instruction, the destination operand is mentioned as a register, while the source operand is the name of a register, R3, and this R3 contains the memory address, and this is the memory address, that is 54, which actually contains the operand. So this is how the register indirect addressing mode works. Well, dear students, for 1 GB bytes of memory, if we want to encode the memory address directly inside this instruction, we need at least 30 bits. And if the memory is larger, we need more number of bits to encode the address of this memory inside the instruction. So instead of doing that, we keep the address of the memory, that is this 54, inside a register, and we keep the register number inside the operand. So this reduces the size of the instruction. The disadvantage of this register indirect addressing mode is that a bit of computation is involved. That is, you first need to access the register, read the register contents, and then present this address to the memory to get the actual operand residing over here. Well, in auto-increment addressing mode, the effective address of the operand is the contents of a register specified in the instruction. It is called auto-increment because after accessing the operand, the contents of this register are automatically incremented to point to the next operand in memory. It is useful for stepping through arrays in a loop. Suppose that this is the instruction. This is equivalent to this high-level language code. First of all, the contents of R1 register and the memory pointed to by the R2 register are added and placed in R1. And after this operation is performed, the R2 is incremented with a value, where this value D is the size of an element. So you can always keep the base address of an array inside the R2 register and follow this auto increment addressing mode if it is available in your processor architecture. While in auto increment addressing mode, one register reference, one memory reference, and one ALU operation is required to access the data. So it is a bit expensive. Similar to auto increment, we have the auto decrement addressing mode as well. And the only difference is that in auto decrement, before accessing the operand, the contents of the register are decremented and then used as the effective address, which is shown over here. You can note that in case of this instruction, the contents of R2 are first decremented and then the resultant value is used to access the memory and add the contents to whatever register there is, that is R1. And over here as well, one register reference, one memory reference, and one ALU operation is required to access the data. Well, after this auto decrement, we have the memory indirect addressing mode. In memory indirect addressing mode, the address inside the instruction over here contains the memory address 128, which instead of containing the data further contains the memory address, which actually contains the operand to be operated on. And this memory indirect addressing mode is used to implement pointers and passing parameters to functions. The advantage of memory indirect is that you can access large memory address space using this mode, and the disadvantage is that it is slow, since you need two memory accesses to actually get the operand. Let me say that x86 does not support memory indirect addressing mode. After memory indirect, we have another category of addressing mode called the displacement addressing mode. In displacement addressing mode, the operand is of course at some memory location whose effective address is the sum of some register content and a constant value in the instruction itself. So this is the instruction. It contains the register code, and the register value is added with some immediate value residing over here, and the resultant value is actually the effective address. So there are three categories of displacement addressing mode: relative addressing mode, indexed addressing mode, and base addressing mode. Let's see them one by one. Well, relative addressing mode is also called PC relative addressing mode and is used in branching, that is, transferring the flow of control of program execution to an address other than the next in sequence. Well, consider this jump instruction, jump 100. Well, dear students, in case of a 64-bit machine, we need to mention a 64-bit address over here, which will of course increase the size of the instruction. This PC relative addressing mode helps to keep the instruction size small. So inside the instruction, instead of giving the 64-bit target address of next instruction to execute, we just give the offset inside the instruction. This offset is added to the existing contents of the program counter register to get the actual jump address. Do note that the jump instruction is at address 4686, and since PC always points to the address of the next instruction, so it will contain 4687 as shown over here as well. Therefore, if the programmer wants to jump 100 bytes ahead of this location, the offset should be set to 1 less than that. So that is why you can see a 99 over here instead of 100. Well, index addressing mode is used to access elements of arrays. In index addressing mode, the effective address of the operand over here inside the memory is generated by adding a constant value to the contents of some register, some index register. Consider this memory snapshot and suppose that this represents a character array. The base or starting address of the array is 1000, 1000, and suppose that we want to access the fifth element of the array, zeroth element, first, second, third, and fourth. So this is the fifth element at address 1004, and suppose that we want to access this element. So instead of giving the 64-bit address over here in the instruction, we keep the base address of the instruction, that is 1000, inside the index register, and the offset of the element as an immediate value inside the instruction. And the sum of these two values give us the effective address where the operand resides. So like PC relative addressing mode, the index addressing mode also help address large memory sizes by keeping the instruction size small at the same time. Well, dear students, other than the implicit, immediate, direct, register and register indirect addressing modes, this slide shows the x86 displacement addressing mode. And these are the four components that can be used together to compute the 64-bit effective address of an operand. The base address, which can be a register or a variable name, that is some memory address. The index register, which has to be a register multiplied with a scale value. The scale value can be 1, 2, 4 or 8. Default is 1. And then the displacement, which is an immediate value or offset normally limited to 32 bits. So these are the four values which together generate the 64-bit effective address inside x86 64 addressing. Well, this instruction is an example that use the base address only. A giant or quad word is moved from memory to this RAX register. The memory address is there inside the RBX register. So we have just used this base address out of these four components in this example. And in this example, we have used the base address with displacement. The base address is there inside the RBX register, and we have added a displacement of 1 to 8 to the contents of RBX register. So the sum of these two values generate the effective address, and a quad word from that memory location is moved inside RAX. This instruction, now this is the third instruction. This is an example that use the index register with displacement. Remember, with the index register we can use a scale value of 1, 2, 4 or 8, and if nothing is mentioned then 1 is the default scale value. And this instruction use the base address with the index register and a scale value of 4. And finally, this instruction is an example that use all the four components to compute the effective address. The base address, which is there in RBX register, the index register is multiplied with the scale value of 4, and then this is added with the displacement value of 50. Okay, let me further illustrate with the help of an example and see how we can use these addressing mode to access the elements of an array. Okay, so consider this assembly instruction ARR DD blah 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 that defines four double variables named ARR. Also note that although double, but each element contains just 1 byte of data, and of course the remaining bits will be set to 0. Assuming that the system is little endian and the base address of the array is shown over here as 1000, this is the snapshot of 16 bytes of memory: 1000, 1001, 1002, 1003 and so on to 1015. The base address of the array is this. So this is the first element of 4 bytes at address 1000, 1001, 1002 and 1003. These are the 4 bytes of the first element, and naturally since this is a little endian, so 65 is placed at the lowest address, and the upper 3 bytes contain 0. And similarly, this value 2a is the first element, and then we have 3 zeros, and this is the third element, and this is the fourth element at index 3. Okay, well, the simplest way to access the first element of the array is shown over here, that uses the base address of the array. We have just used the base address of the array, and the contents of that location will be placed in EAX. So the contents of ARR sub 0, this 65, rather this 00000065 will be placed inside the EAX register. One can use these two instructions as well together to access the first element of the array. We have placed the base address of this ARR inside RBX, and then we have read the memory contents and placed them in EAX. Now this is one possible way to access the third element of the array. It uses the base address plus displacement. The base address is 1000, displacement is 8. So we move on to 1008, which contains the third element of the array, ARR sub 2. And this is another way to access the third element. First place the base address of the array in RBX register, then place the displacement, that is 8, inside the index register RSI, and finally use the base address plus index register to compute the effective address. And yet this is another way to do the same task with the base address in ARR over here, element to be accessed in index register, that is 2, and multiplying the size of each element as a scale factor. So these are the x86-64 displacement addressing modes. My dear students, once we will be studying the arrays in detail in some future session, we will again fall back to this, and we will practically see this how it works inside our famous GDB. Okay, dear students, that is all what addressing modes are. This is one of the most important topic of computer organization and assembly language programming. Last but not least, remember every processor has its own set of addressing modes. And today we have talked about them in general, and I have touched upon the addressing modes of x86-64 as well. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. Wish you all the best, happy learning, and Allah Hafiz.